So here we have an example of the interference of two sound waves in a two-dimensional problem. So we have two identical sources that are producing waves that are moving sinusoidally away from each of these, but are in sync with each other. They're in phase with one another. So here's speaker A producing a nice sinusoidal wave going around here to this point C here. And then speaker B moving along as well and producing also a sinusoidal wave that is in sync, in phase with it. In this question, we're asked to find out whether this listener here will hear a loud sound, which is basically constructive interference, or no sound at all, which would be destructive interference. And you're told that the listener is standing at a distance of 2.4 meters from speaker B, and speaker A and B are separated by a distance of 3.2 meters, forming this nice triangle ABC. Both speakers are playing the same frequency, 214 cycles per second, or hertz. We're also told that the speed that they travel at is 343 meters per second. That's the speed of sound. Now, to determine whether they're in sync or out of sync with each other, we really need to find the path difference between the distance that speaker A goes to the listener and speaker B goes to the listener, and compare that path difference to the wavelength of the sound. Now, the wavelength of the sound wave is not given, but you are given the frequency and the speed. So hopefully you recall that the wave equation is the speed equals frequency times wavelength. So therefore the wavelength is speed divided by frequency. So 343 meters per second divided by a frequency of 214 hertz. This means that our wavelength of the sound wave is about 1.60 meters. So the next thing we need to do is we need to find that path difference. So let's say A travels this distance here to point C, we'll call that R sub A. And speaker B travels this distance right here, and we'll call that R sub B. The path difference is the difference in distance that each of these speakers would travel. We're going to call that delta R. So take the longer distance, which is R sub A, minus the shorter distance, which is R sub B. But it looks like we're going to have to determine R sub A here because it's not given, and hopefully you recall you could figure that out. Since it's a nice right triangle here, you can use Pythagorean theorem. That would be 3.2 meters squared plus 2.4 meters squared, the sum of those two and the square root of that. So that gives you a distance of exactly 4 meters. Okay, so the path difference will be 4 meters, that's 4 meters here, minus this distance here, which is 2.4 meters. So that means that our path difference is 1.6 meters. All right, and we know our wavelength is, compared to our wavelength we just determined, is 1.6 meters as well. So what does that tell you? We see that delta R is exactly equal to the wavelength. Thus, this means they're essentially in sync with each other. So it means that we have constructive interference. Now, if, for example, delta R was, say, half of this, like 0.8 meters, then we would have destructive interference. So remember, constructive interference states that delta R must be equal to m times lambda. And in this case, m is equal to 1. So hence, the listener hears a loud sound. There'd be some great extensions to this problem, like what other positions would result in constructive interference? Does he have to stand exactly in this place, so this triangle? Well, he could be like maybe midway, as long as these two distances could be actually the same. And then in that particular case, the delta R would be 0, and that would be constructive interference as well. So constructive interference would occur at any point where that path difference is equal to a multiple of this number. Now, if you were to get no sound at all, you would want that path difference to be equal to, over here I'll just write it, delta R must be equal to m plus a half times lambda. So you could kind of work it out and say, okay, what would if I put m equals 0, then half of lambda, put lambda 1.6, so delta R would be 0.8 meters. Or you could put m equals 1, and then you have 1.5 times 1.6 wavelengths, and you can find out the delta r. So there'd be a variety of examples, situations where you would get constructive and destructive interference. All right, I think that's it for example 2. You should try out some of the problems that deal with that are similar to this in the homework.